Hello, my name is Markus Sommer, and this is Josef Stepandic, and the two of us together are now going to present efficient generation of a digital twin by using methods of artificial intelligence. A warm welcome from my side as well. My name is Josef Stepandic, as has just been said, and we would like to present our two companies. And I will start with ISB, which was founded in 1996. We are based on the banks of the Lake Constance, and our main points of focus are electronics, software development, and artificial intelligence. In artificial intelligence, we're particularly active in the production of digital twins and optimization using evolutionary algorithms. I am the business manager. And I work for ProStep AG. I have been working there for almost 25 years in various positions. As I'm sure most of you already know, ProStep is 25 years old. That means that I have been accompanying ProStep almost right from the beginning. Looking at this, how did we end up talking about artificial intelligence and generating a digital twin? Using classical methods going back to the 60s or even the 50s, production, which is where we are mainly positioned now, was based on measuring tapes, 2 meters long as you know them, and photographs if there were any even, and then all that was drawn by hand by a draftsman. The next step then was closely linked to laser scanners and implementing a point cloud in a CAD model. And everything seemed rather unwieldy and it isn't really up to date. And that is why now you can scan using a laser scanner, but other methods are also available. We'll present them later on. And what ProStep does predominantly is object recognition within these point clouds. And that way we can shorten the production process of a digital twin by, well, approximately half. Josip, what's your view of this? Well, we have been confronted with this topic for many years now. And often enough, we were lectured that the so-called remastering, that means the manual structuring of the models, is something you couldn't get round. And it's difficult to believe that these days, with all the IT technology we have, there was no way to do it differently. So we said, we'll just make use of this joint project to address this topic using artificial intelligence. That means we record reality in a point cloud, a more or less homogeneous point cloud, and then we use suitable software methods based on artificial intelligence, and that way we can recognize, as the human eye would recognize, what is present in a hall or a scene. We joined forces with ISB and ProStep, the Institute for Production and Tools in Hanover, and Bonnemann from Dellingsen. And we just considered how you could get from a real physical production system to a digital twin. We identified 3 blocks to begin with. Scanning is important, generating a point cloud. Perhaps you want to give us a deeper insight later on. Then interpreting the point cloud and object recognition based on objects in the reference database for recognizing objects and creating an assembly for the production system. And then, when this CAD model is available, you can expand that using an XML interface or other interfaces as well, and use it in a simulation system. here our simulation model, and as soon as that has been set up, you have a digital twin. On one side the production system, on the other side a digital image of that. Mostly in all of these systems, they can only be as good as your starting point, as the original values. And if you look at object recognition, what would a point cloud have to look like in the end so that you can actually use it? You're absolutely right. You can't just take any old thing and think that any old point cloud would allow you to recognize things. To begin with, it has to be a homogeneous point cloud. That means without major gaps, because the methods for object recognition cannot process that. You need to have positional accuracy. That is quite significant, whether a machine is half a meter to the left or to the right. Often in a factory, you have a margin of a few centimeters, and then further procedural structures have to be given, like for instance consistency of particular data formats, etc. But at the end of the day, what's important is that you have good input to make it work. And I would like to transition right into the scanning process. At the beginning I said there were laser scanners, and you can also measure by hand, and we have now focused on the issue of 360 videos. Why have we done that? Because these days 360 videos can be generated quite easily, and they can be generated everywhere. You can record them wherever you like, and you can also get these products everywhere. So the potential customer can walk through his production hall with the 360 camera and record a video, and we want the whole thing to be pragmatic. So that means he would upload this video to the cloud, and we extract individual images, edit those, for instance for noise reduction or color matching, and then these individual images are fed into a specific 360 photogrammetry, and using these pictures a point cloud is generated there. And this point cloud can be viewed, but as we will see later on, it can also be passed on for object recognition. Joseph, do you believe that a customer of yours would do something like that? Of course. For the process we illustrated at the beginning, the quality of the point cloud is decisive, irrespective of which device they've been put out of. If we have sufficient accuracy, a high-quality point cloud, it doesn't matter which device it was delivered by. There is a plurality of devices, and for further processing that is then perfectly sufficient. Great. Then I would like to talk about our devices that we have tested and the ones we've used. What does the customer do when he has such a device? He takes the tripod and screws this 360 camera onto this tripod and walks through the production site with this tripod. And why did we choose these products? Because if you go further down, then the image quality is often not quite as good as it should be. And subsequently then we end up with problems in generating a point cloud. Now if I look at the recording times at the bottom, 40 minutes and 80 minutes, and also the resolutions, what do you think? Is that a good resolution? These are very good parameters, and that's quite promising. both the resolution and also the recording time are actually within the range, which would be significantly better than most other devices. As already said, there is a whole plurality of devices, and the ones described here are characterized by high flexibility and high accuracy. So you should not fall for the illusion that you can use a normal simple device at a good price and expect high quality. Normally, and we engineers know this, everything is a trade-off of several parameters. But I would still like to address laser scanners and 360 degrees, because our customers would say, okay, I need high precision and I need a laser scanner. Yes, the laser scanner at this time is in use in production, but when you look at this, the investment in a laser scanner is quite expensive. You need quite a lot of time as well, and it has to be done by an expert. And that gives you an accuracy of a millimeter at the end. Now the question is, do I really need that kind of accuracy later on? Or would it be sufficient to have a margin of error as a centimeter? And if I reduce my requirements at that point, now in construction sites you can see that often you have a margin of tolerance of half a centimeter even. So with a 360-degree camera, I'll be much more efficient. And that also gives me smartness and simplicity. And also a 360-degree camera means I don't have to go back there with my laser scanner. A salesperson who's visiting a customer could make a recording, and then 1 or 2 days later I would already have my point cloud and I wouldn't have to go there again. Josip, what do you think, particularly with respect to this accuracy? Would that be acceptable for your customers? Yes, that's perfectly acceptable. What is stated at the moment, a few centimeters in a factory isn't that relevant. The question is how you'd actually test accuracy of such devices. But what's important for any kind of positional accuracy in a factory is that the deviation isn't too great. The assumption is that you have very good software so that you can generate a point cloud based on these recordings, which evidently you have, and that way the problem is solved. And the customer can be happy about it. Okay, that takes us to the next picture. You've taken a great picture, you've created a point cloud, and what do you do with it then? We've said we don't want to remodel, we actually wanted objects in this point cloud, for instance, of a factory hall. We want to recognize the objects that are actually there in their right position, also in the right position. How would we do this? We said this is the era of artificial intelligence, and there are a whole lot of different methods which can be used, for instance, autonomous driving, etc. Generally speaking, we're talking about convolutional neural networks, and they are generally made up of 2 steps, training and testing. That means, roughly speaking, to begin with, you have to tell the system what objects we're looking for, a machine of a particular manufacturer, a particular version of it, and then the geometry of this object, the formats, and then you search for this object, and that takes place in 3 consecutive steps. To begin with, segmentation. What is segmentation? That is basically breaking down this point cloud into several segments. Partial point clouds, you can see that denoted by the different colors. When we're talking about a factory, you have different categories such as floor, walls, ceiling, machines, conveyors, lines, etc. In total 9. Of course, it could have been 19. That might have made the whole thing a bit more even too complicated. That means that you can structure the problem better and you can address the objects you're really interested in. Once this step has been done, you stay in the point cloud, but this is then broken down. The next step is clustering. Each segment is taken and searched for clusters of points in the point cloud. When you look at it, then you see individual objects in this point cloud format, and then this cluster is delimited by a cuboid, the so-called boundary box. That's then defined in space, and we're talking about accuracy here. For this we need positional accuracy. Once this step has been taken, then we reach the actual object recognition. We call that classification because it occurs based on certain statistical methods. Statistics tells us with a probability of 97.3%. Within this one cuboid, you will find a Müller & Sohn machine of this and that type. And that means we have found the right object in the right position. Should anything have happened, you might see that the object has been turned because we have 24 position. We can talk about rotated by 15 degrees, or something else has happened. The wrong object has been given the wrong name. When this method has been completed, you receive a list of all the objects which have been found in this hall, in this point cloud, together with the probability based on which you can say with 90% accuracy that the object has been found, together with the point and the vector in space. But I haven't heard anything of a CAD model yet. To me that sounds like I only get a list of objects. Here we're moving in space with simplified data, point clouds, and object search. When we have found the right object, the machine we're looking for, then we'd get the CAD model from the library, which we already have, and put this object in the right position in the assembly, which we have set up specifically for this factory. That means we have a template for the whole factory. Here we have our plant total. You could work with any system, of course. And then we have a structure, the skeleton model of our template, and further structuring for the individual plant, and then you can find subgroups for each of these categories, and that then can be continued as you please. But it has to be said that this structuring should be decided on in earlier stages so that object searching will only occur based on these categories. Now, when all of this has been completed, then in the CAD system you are given a complete result with the assembly, with all the individual components in this structure with several sub-assemblies. And the user knows when he's looking for a machine in the factory, he will find the sub-assemblies with the machines, and there he can find his machine again. But in our case, many customers want to structure things differently. If I have a building, then I might not want to have the walls and the floor, but possibly the machine together with the floor. Is that possible as well? Of course that is possible as well. The result is a total result. That means we're looking for everything that there is in the hall, and the result is complete. But the situation with customers can be different. For a simulation which will follow then, because we export the data to the simulation system using XML, in one simulation, machines and lifting devices might be necessary. For further design, if you want to restructure the factory, you might need the walls and the ceiling after all. We have tried to generate a more general structure, but if the customer comes along and says, I want to differentiate between different types of machines, then in an early stage, probably already in segmentation, we can structure it that way already. That sounds great, particularly the flexibility is given here. What is important is that we're starting with hundreds of gigabytes of data. At the end of the day, the customer will receive his CAD model in normal size. What's important is that the customer picks precisely the application he needs and he will get the data he needs. But then finally, in his CAD model, he can measure a lot with a certain degree of accuracy. But many of our customers also say, I've got a CAD model, it's quite nice, but it's not much use. And that leads us to the next step and also the last step, at which, together with the CAD model, we carry out different steps and analyses. And here we have a few possibilities for analysis, and what we see more and more of is right at the bottom at the moment. How can material transport be done efficiently using autonomous driverless transport systems so that my factory can be managed more efficiently at the end, also keeping in mind future production programs if I have a batch size of 1 later on. Josip, how do you see it? What do your customers say? Is that a good result? Or would they say, I need another point down at the bottom because that's really important to me? There could be further points at the bottom. We have spoken to turnkey suppliers. They have totally different applications, but what's important is we have a structure ready to use, and where we started in the second or third slide, the customer has the choice, either to structure it all manually, manual remastering, or he can use an automated method as we have presented it here now. And for the customer, it is easy to illustrate that each step which he wants to carry out manually can be carried out automatically, much faster and at lower costs, and that is the benefit for the customer. In order to explain this benefit to the customer, we have thought of a concept to commercialize it. This is an extension of opendesk.com, which customers have been using for 23 years. This object recognition can be seen as an extended form of CAD data conversion from the point cloud to a specific CAD model. That means the customer has to be able to record his production system anywhere in the world with the devices and methods which you've presented. That is ISV's method, and then the point cloud is generated and transferred to OpenDesk, where the subsequent steps, object recognition, upgrades of objects, or translation into a particular format occurs, and then the data are exported either to factory planning, where amendments have to be carried out, or straight to process planning, where these processes like bottleneck analysis can be carried out. And that way the customer receives a service from us from one source which addresses his specific problem in a digital twin. And that means we've already reached the end of this presentation. And if you have any further questions, here are our contact details. Feel free to address Jopit Stepandic or me. Thank you very much for listening. Thank you from my side as well. We'd be very happy to hear from you.